Whenever we hit a wall with a massive, complicated problem, something way too complex for one person to figure out, we all share this deeply ingrained reflex. We break it down. We slice up the work, we isolate the components, and we divide the labor. It's kind of the foundational logic of modern civilization, right? From assembly lines to global supply chains to massive digital networks. Complex tasks require division. It reads like pure common sense. We treat this almost like a natural law of human organization. If you want any system to scale up, you just have to divide its operations into smaller, manageable, highly specialized little pieces. It's a calm, observable mechanistic tendency. We divide to conquer.
But when we actually look at real-world systems operating at scale, think healthcare networks, massive corporate databases, global logistics, we see an immediate, glaring contradiction. Highly divided, specialized systems, they don't run flawlessly. In fact, they frequently, predictably, and catastrophically collapse. And here's the fascinating part. They don't collapse because the individual parts are broken. They collapse because the parts are isolated.
So this brings us to a deeply counterintuitive observation, and it's absolutely crucial if we want to understand how the world actually works. Local success often guarantees global collapse. The invisible structural force driving a system into ruin isn't human error. It isn't bad management. The failure is actually driven by the system's relentless attempt to improve itself. To see how this happens, we need to watch a physical system in motion.
All right, Section 1, the efficiency contradiction.
Okay, to really grasp the mechanics of this collapse, let's picture a continuous physical system. Imagine a massive central conveyor belt moving at a steady, relentless pace. It's feeding this chaotic, messy mixture of raw materials, just totally random shapes, sizes, and weights, into a series of independent mechanical sorting gates. Now, at this early stage, the gates are wide open, and you can clearly see the entire flow of material moving across the factory floor.
Moving on to Section 2, local optimization. Now you might be wondering, why would we ever divide that continuous flow into isolated gates in the first place? Well, consider the rational incentive historically captured by this staggering number, 48,000. Back in 1776, Adam Smith observed a pin factory. He noted that if a single, unspecialized worker tried to make a pin from start to finish, drawing the wire, straightening it, cutting it, pointing it, they'd be lucky to make one pin a day, maybe 20 tops. But by dividing that manufacturing into 18 distinct, separated operations, a small team of 10 men could crank out 48,000 pins in a single day.
I mean, the absolute disparity there is undeniable. 20 units versus 4,800 units per person. This just proves that local optimization, hyper-focusing on a single, separated task, makes perfect rational sense. The efficiency gains are massive. No system designer on Earth can afford to ignore a multiplier like that. The structure literally demands that tasks be divided.
Let's jump back to our physical conveyor belt. Following that exact rational incentive, the system divides. The sorting gates get upgraded, so instead of handling everything, Gate A now only handles squares. Gate B only handles spheres. And because they're hyper-specialized, these isolated gates start processing their specific shapes flawlessly and at lightning speed. Local efficiency absolutely skyrockets.
Which brings us to Section 3, the loss of visibility.
But by hyper-specializing, we trigger an immediate, irreversible physical consequence. The system has traded broad awareness for local speed. Karl Marx actually observed the psychological toll of this extreme division, noting the operator becomes depressed spiritually and physically to the condition of a machine. But putting the philosophy aside for a second, this is a profound structural insight. Extreme division completely removes the operator's connection to the larger process. They no longer know, or honestly even care, what the whole system is producing. They only see their tiny, repetitive fraction of the work.
And we can literally watch this loss of visibility manifest in our physical system. To prevent distractions and squeeze even more speed out of the sorters, physical chute walls are constructed around the individual sorting gates. As the gates process faster, the walls rise higher. So now, the gates are highly efficient, but they're completely walled off. They can't see the main conveyor belt anymore. They can only see whatever drops directly into their specific isolated chute.
All right, Section 4, the coordination trap. Here's the trap. Divided systems require intense coordination, but their brand new, isolated structure actively prevents it. You can model this dynamic by looking at the classic stag hunt game. Two hunters have a choice. They can coordinate to hunt a stag, which yields a massive reward,
but it requires risky, perfect timing. Or an individual can safely just hunt a hare alone, yielding a small but guaranteed reward. The coordinated yield is way better for the whole system, but it strictly relies on trust and broad visibility.
So what happens when visibility drops? Safe isolation predictably outcompetes risky coordination. The local units operating entirely rationally inside their walled-off environments are always going to choose the safe, isolated option. They can't see the other hunters. They can't see the main belt. Therefore, any attempt to coordinate is mathematically just too risky. They will optimize only for themselves.
Look back at our physical system. Suddenly, the main conveyor belt changes its output. It starts sending down these large, brittle glass triangles. But the blind sorting gates, walled off inside their chutes, cannot see this change coming. They just operate flawlessly according to their local programming. So the mechanisms smash the glass, perfectly sorting the shattered pieces into the wrong bins at record speed. They are effectively destroying the output, not because they are broken, but because they simply cannot coordinate.
And that takes us to Section 5, irreversible structural lock-in.
The tension in the system has completely peaked now. The local components are operating with absolute perfect efficiency, yet the overarching system is failing spectacularly. And the terrifying part? The system has now become entirely rigid. It is incapable of escaping its own architecture. We can finally name the mechanism at work here, the information silo. But listen, an information silo is not a management failure. It's not an accident caused by lazy employees who just refuse to communicate. It is an insular subsystem incapable of reciprocal operation. It's the mathematical inevitability of divided labor. When you divide tasks to optimize them, you have to build walls. And when you build walls, you trap information.
Let's methodically trace these escalating constraints one last time. Step 1, tasks separate to increase efficiency. Step 2, because those tasks are separated, visibility across the system drops. Step 3, without visibility, local goals diverge from the global goal. Remember, it becomes safer to hunt the hare than the stag. And step 4, the system locks. The individual parts become so incredibly specialized and isolated that they can no longer communicate, even if they desperately wanted to.
We see this perfectly in the final state of our physical system. The sorting gates are now completely enclosed in thick steel. They are operating in a perfect, high-speed vacuum. Inside their silos, their performance metrics are absolutely flawless. But meanwhile, outside the silos, the factory floor is just buried in shattered glass in missorted ruin. The parts are succeeding, but the whole is dead.
And this brings us to a chilling realization that basically reframes everything we've looked at in this explainer today. When large, complex systems break down into isolated, uncommunicative parts that destroy the overall goal, the system isn't actually failing. It's behaving exactly perfectly as its divided structure dictates. The structure itself mathematically demands isolation, which leaves us with a terrifying question. If our most vital global systems are mathematically programmed to isolate and collapse, how much of our modern world is already functioning as a perfectly optimized corpse?